Friends, welcome to this new video. In this video we can see general test for convergence at infinity. It is also known as Cauchy's test at infinity. Point of Cauchy's test, general test at infinity, is the integration of f converges at infinity if to every epsilon greater than 0 there exists a positive number x0 such that mod of integration of f between the limit x0 x1 to x2 is less than epsilon. So friend, we know that, let us prove this. We know that the integral a to infinity f dx exists if limit of integration of f between the limit a to capital X tends to infinity exist, and therefore we consider let this is a function of capital X, so we write it as capital X equal to integration of f between the limit a to capital X. Then capital F of X is a function of capital X, and by Cauchy's criteria we know that the function for epsilon greater than 0 there exist numbers x1 and x2 such that mod of f of x1 minus f of x2 less than epsilon, or there exists x0 such that for all x1 comma x2 greater than x0. But what is f of x1? This is a to x1 f dx integration minus a to x2 f dx less than epsilon, or same thing as integration x1 to x f into dx integration x1 to x2 less than epsilon for all x1 comma x2 greater than x0. So this is the proof of the general test for convergence at infinity. We have applied Cauchy's criteria for a function limit of the function f capital F exists if for every epsilon greater than 0 there exists x0 such that mod of f of x1 minus f of x2 is less than epsilon. Now depending on this theorem we prove examples, we solve examples show that integration of sin x divided by x between the limit 0 to infinity is convergent. We know that since limit of sin x divided by x tends to 0 is equal to 1, 0 is not point of infinite discontinuity. Okay, therefore we take integration 0 to infinity sin x divided by x into dx equal to integration 0 to 1 sin x divided by x into dx plus integration 1 to infinity sin x divided by x into dx. And for the second we can apply the Cauchy's criteria a to infinity. Then for every epsilon greater than 0 let we consider these two numbers x1 comma x2 be two numbers both greater than 2 divided by epsilon, right? means x1 is greater than 2 divided by epsilon, x2 is greater than 2 divided by epsilon. This implies 1 divided by x1 is less than epsilon divided by 2. 1 divided by x2 is less than epsilon divided by 2. By Cauchy's criteria, therefore, integration mod of integration x1 to x2 sin x divided by x into dx equal to let us integrate sine as a x as a first function and sine as a second. 1 divided by x into integration of second minus cos x between the limit x1 to x2 minus integration of 1 divided by x into minus cos x and integration of this derivative of first x square into dx between the limit x1 to x2, and this is in the modulus value. Okay, this is in mod. So this is equal to, you can see that this is cos of x2 divided by x2 minus minus plus cos of x1 divided by x1 minus integration x1 to x2 cos of x divided by x square, and it is in the mod. This is less than equal to mod of cos x2 divided by x2 plus mod of cos x1 divided by x1 plus mod of integration x1 to x2 cos of x divided by x square into dx. Okay, then see the first term, cos, maximum value of cos is 1, therefore this is less than equal to 1 divided by x2 plus 1 divided by x1, and also the cos x divided by x square is less than equal to, maximum value is less than equal to, this is plus here, plus x1 to x2 dx divided by x square. This integral, this 1 divided by x1 plus 1 divided by x2, and this integral is a very again a small value. So this total three terms will be less than epsilon by 2 plus epsilon by 2, and epsilon by 2 plus epsilon by 2 is nothing but epsilon. So this shows that mod of this function, say x1 to x2 sin x divided by x into dx is less than epsilon, and hence by Cauchy's general test at infinity, the integration, therefore integration 0 to infinity sin x divided by x into dx is, first, the definition of absolute convergence. The improper integration a to infinity is said to be convergent, is absolutely convergent if integration of mod f is convergent. In the continuation, we see the theorem, if a function phi is bounded in semi open interval a to infinity and integrable in closed interval a comma x, where capital X is a number greater than equal to a, and if integration of f is absolutely convergent at infinity, then integration of f into phi is also absolutely convergent at infinity. Now friends, it is given, what is given? Phi is bounded. Phi is bounded, therefore there exists a number capital K such that mod of phi is less than equal to k for all x greater than equal to a. Again, we know that integration a to infinity f dx is absolutely convergent at infinity. That is, integration a to infinity mod f is convergent. As it is a convergent, it is bounded. It is bounded. That is, there exists in a number capital M such that mod of this integration a to infinity f dx is less than equal to capital M. Here modulus is, that is here mod f is less than equal to x, right? And that means here we have not infinity, but we take here capital X. This is for all x greater than equal to a. Now if we consider the product function phi into f, therefore mod of f into phi is less than equal to k into mod f. Then if we take the integration a to x mod of f into phi into dx, this is less than equal to k into integration of mod f, but this is less than equal to k into m for all x greater than equal to a, and hence this function integration f into phi between the limit a to infinity is absolutely convergent